In Against Measurement, Bell's 1990 paper, that's John Bell, he emphasizes that the problem of measurement, the so-called measurement problem in quantum mechanics, lies in the unrefined notion of measurement. He delivers a sharp critique towards imprecise concepts, and this is a quote from page 34, I think. Observation is a complicated and theory-laden business. Then that notion should not appear in the formulation of fundamental theory. Information? Whose information? Information about what? End quote. So in philosophical discussions about philosophy of physics and philosophy of mind, I guess we should define when information is being used in a technical sense. So for example, classic information theory was first formally characterized by Shannon in around 1948. Bell develops his critique, what exactly qualifies some physical systems to play the role of measurer. Was the wave function the world waiting to jump for thousands of years until a single-celled living creature appeared? End quote. So measurements are interactions between physical systems. These systems, entities, or observers of varying complexity can always be characterized by information. That information is always in another physical entity and about the other physical entities constituting the environment. A physical entity can be characterized by its boundaries separating it from the environment, and I guess just to reference it, Quality Research Institute, so Andres Gomez Emilson and Chris Percy, I believe it's like a 2025 or 2023 paper where they talk about the topological segmentation of electromagnetic fields as addressing the so-called boundary problem in consciousness studies, which is, why is our experience bounded to these certain phenomenal fields attached with these certain bodies that we do have. In differentiating the landscape of quantum theories, there's certain monumental papers, one of them being the Einstein-Podolsky-Rosen paper, sometimes referred to as the EPR paper, titled Can Quantum Mechanical Description of Physical Reality Be Considered Complete? This was written in 1935. So they articulate a central conceptual tension. Quantum mechanics predicts perfect correlations between measurements on entangled systems, regardless of spatial separation. That's something that, for example, has been experimentally verified and is, I think, the result behind the 2023 Nobel Prize. So, due to these Bell-type inequalities that result from the EPR paper, Bell's paper ultimately, they claim that one of the three statements must be true. Firstly, either locality is violated. So locality refers to a fundamental postulate of reality that the speed of light sets the universal speed limit. So for physical reality to be non-local would mean that a measurement at one place could superluminously or instantaneously, faster than the speed of light, affect a distant measurement on an entangled system. So a lot of our modern physics depends on, in relativity at least, it gives us our kind of best notion of causality that we have. Quantum mechanics gets really complicated there, but in relativity we have like light cones defined by the speed of light, and we have things that are space-like and time-like separated. So just learning relativity to understand that more. So statement number 2 that could be true or false, or that one of these three statements must be true. These three radical claims, I'll just list them off now for reference. Locality is violated, realism fails, specifically their criterion of realism, or quantum mechanics is incomplete. So realism fails would mean in this specific paper, realism is the notion that measurement outcomes reflect pre-existing properties of the system, or alternatively, outcomes aren't so-called created by the act of measurement. So specifically, their EPR criterion of reality states that if we can predict with certainty the value of a physical quantity without disturbing the system, then that quantity corresponds to an element of physical reality with a definite value independent of our interaction with it. Third statement, quantum mechanics is incomplete. This would mean that additional elements are added to the formalism. Now that these foundational assumptions are explicit, the structure of the theoretical landscape, in other words, the competing quantum theories, can be kind of laid out. The ontological models can actually be differentiated based on how they respond to a family of Wigner's friend thought experiments, originating really with Schrodinger's cat in 1935, later developed by Everett in his 1957 thesis, and also Wigner in 1961 into illuminating self-referentiality problems. So consider Heisenberg, a scientist sealed in a laboratory measuring the spin of a qubit. For Wigner standing outside, the entire laboratory is represented by a quantum state that evolves unitarily into superposition of all the outcomes Heisenberg might observe. This might sound crazy, but if you kind of look at the mathematical formalism, that's really what's being referenced here. It's ultimately built off of linear algebra, which I think most people can and probably already do understand to some degree. But if Heisenberg experiences a definite result inside of that lab, what becomes a Wigner state? Remember, Wigner is outside of that sealed laboratory observing Heisenberg. Must a Wigner state collapse when Heisenberg observes an outcome, when Wigner observes an outcome, or is there never a collapse? If there is a collapse, what law characterizes it? Is it deterministic, or is it not? Is it related to consciousness or gravity in any sort of way? So roughly, there are four broad ontological interpretations of the quantum formalism. I think before I get into this, I'll straight off the bat say that I think epistemic views are typically underappreciated compared to other views. So this is basically a rundown of some of the most popular views on quantum theory. This is by no means exhaustive. There are many very excellent and plausible theories that are not being adequately covered, and these theories aren't even being adequately covered, but here we go. So there is hidden variable or modal theories. So if one preserves universal unitarity while insisting that measurements have a single actual outcome, then the quantum state must be incomplete. There must be additional elements of reality not encoded in the wave function. So the de Broglie-Bohm pilot wave theory exemplifies this strategy by supplementing the wave function with definite particle trajectories guided by non-local law. So this is in Bohm's 1952 paper. It's a two-parter. And there are many world theories, also known as Everettian theories. So if the Schrödinger equation is treated as a complete description of physical reality and unitary evolution is universal, then all measurement outcomes are realized in branching, decohered components of the universal wave function. There are collapse theories, so if the quantum state inside the laboratory truly collapses contrary to unitarity, and it's not due to Wigner's observation, then some objective dynamical mechanism must trigger the collapse. So naturally that gives rise to the Girardi-Riemannian-Weber theory. So they have like a 1986 paper. And there's also the, I think, continuous spontaneous localization is related. I'm not really sure about these things. And then there's also gravitationally induced collapse models, such as Penrose, and he has a 1996 paper covering this. There are also relational or perspectival approaches. If measurement outcomes are essentially relational or observer-dependent, then Heisenberg may have a definite result, while Wigner, as a separate physical system, may still ascribe a superposed state to the system. And so this leads to what are called psi-epistemic views of the quantum state. So the quantum state is usually represented by a psi. I mean, it can essentially, in ordinary quantum mechanics, be generally thought of as a vector, just an arrow in space with, I guess, certain number of characterizations. It's a little bit complicated because we're dealing with Hilbert spaces, which are infinite dimensional, but it's really not too crazy, I guess, for mathematicians, I should say. The psi-epistemic views are, I guess, some of the views that I think are more underappreciated, maybe. So relational quantum mechanics is one view, and that's like Carlo Rovelli, and some interesting stuff. And another research program that I would like to highlight is QBism. So that's QBism. Originally stood for quantum Bayesianism, but it's kind of changed. And some people working on that, as like Chris Fuchs, they kind of fit well with other research programs that I'm interested in, so like conscious agent theory, integrated information theory, and other mathematical models of, I guess, first-person experience. So like Quality Research Institute, I think, is one of the best places for that, and they tackle the psychedelic experience and stuff, but that's all maybe for a separate discussion. Yeah, I hope that was a somewhat informative overview of the landscape of quantum theories. I mean, this is really supposed to be kind of like a more academic reference, but just, something that is very interesting, and I hope something stuck and there's a lot of opportunities for further research.